the highly radioactive liquid from Chalk River, Ontario, to the Savannah River site, which is an old military complex down in South Carolina. They used to make the plutonium for the warheads for the atomic bombs. And in fact, they have a particular facility where they actually used to separate that plutonium. And that's where the high-level radioactive liquid from Chalk River is going to be going. It's called the H Canyon in Savannah River, at the Savannah River site. I'm sorry, in South Carolina. So Chalk River Laboratories is up north of Ottawa, on the Ottawa River, as you know, and they have been producing medical isotopes for many years. And in the process of doing this, they irradiate highly enriched uranium. This highly enriched uranium comes from the United States. It's weapons-grade uranium. It's the same stuff that was used in the Hiroshima bomb. And they put small samples of that, called targets, into the reactor there, the NRU reactor. And then when they pull it out, it's very, very radioactive. It's very similar to spent fuel in the sense that it has all these fission products, all these broken pieces of uranium atoms that come by all different names and which are much more radioactive than the uranium itself. They then dissolve that target in nitric acid and separate out something they want, which is called molybdenum-99. It's one of the broken pieces of uranium atoms, one of the fission products, and that's what they use for medical isotopes. Now, as a result of this, they have a tank containing 23,000 liters of this highly radioactive liquid. This stuff is so radioactive that it's basically unapproachable without very heavy shielding. It gives off a blast of penetrating radiation. It also generates heat, this liquid, because it is so radioactive that that energy is transformed into heat. And so they have to monitor the heat and make sure that the tank doesn't overheat. There's also another problem. Because it has weapons-grade uranium in it, there's a possibility that it could, for a freak accident, it could kind of reconcentrate, and you'd get a spontaneous nuclear chain reaction, which would be very bad news indeed. That's called a criticality accident. So this tank is a double-walled steel tank, and it's full. It's been full since 2003, and now they have struck a deal with the Savannah River people to ship this liquid, this dangerous liquid, all the way down approximately 2,000 kilometers, a little bit less, depending on the route. And you can see some of the potential routes there. It's going to, of course, either cross the St. Lawrence River or the Niagara River, or possibly the St. Clair River over near Detroit. It's got to get from Canada to the United States, and then it's going to pass through dozens and dozens of communities on the way down. And it'll take about 4 years in about 100 to 150 shipments. And here's a typical look at what kind of arrangement they would have. They want the driver to be separated from the container that contains the radioactive liquid so that he doesn't get too much of a radiation dose during his entire trip. Even people beside the canister, beside that container, will be getting some gamma radiation and also a certain amount of neutron radiation coming out from that container, because you can't completely stop that. They have shielding inside. They have lead shielding to stop the gamma radiation. And strangely enough, lead doesn't stop neutrons, but water does. And so they have a layer of water which slows down and prevents all the neutrons from getting out. But anybody nearby, including the driver of the truck, will be getting a certain amount of gamma radiation and a certain amount of neutron radiation. There's also two other types of radiation called beta and alpha, but they are only dangerous when they get out into the environment and really into your body. So they are ingestion hazards, but they're not external hazards. So here's what the actual cask looks like. It's now what it has at the end, it's got these two dumbbell-shaped fittings at the end, which are called impact limiters. And the idea there is that if the package were to suffer an accident and the cask were to fall, then the impact limiter would absorb a lot of the shock and prevent damage to the package body. The body of the package is the one that contains the, inside that package, that body package, they have the layer of lead, the layer of water to shield the gamma radiation and the neutron radiation. And then in the inner cavity, they have, in the past, they had baskets containing solid material, because this cask was designed 30 years ago, and it was ever only used before to transport solid material. This is the first time ever that they've tried to transport high-level radioactive liquid over public roads. They've simply never done this in the 71-year history of the nuclear age. That's what makes this shipment particularly unprecedented. And now here's another picture of the lid taken off that cask, so that you can get a kind of an idea of what it looks like inside. That's cavity is where the radioactive material will be going. There it is again. This simply shows you the package body. The impact limiters are extra things which are put on either end to make that dumbbell shape. And although this is not a great diagram, it sort of shows you the inner structure of the cask, which contains that layer of lead. It contains a total of about 2 inches of stainless steel, all the way from the outside to the inside. Different thicknesses. There's a half an inch thickness, and then there's a quarter of an inch thickness, and so on. And when you add it all up, it comes to about 2 inches of stainless steel. And there's about 3.75 inches of lead to block the gamma radiation. And then there's water. Now those dimensions could change depending on the design of the cask. So there are varieties of this. Here is the inner container that they're going to put the liquid in. And each one of these casks will contain 4 of these steel bottles. And those steel bottles contain the highly radioactive liquid that they're going to be transporting. Altogether, one shipment would have about 232 liters, 232.4 liters. And it'll take, if you just do a little simple arithmetic, you'll see that that'll take at least 100 shipments to evacuate 23,000 liters from the tank. Now, what's in the tank? Well, the data that's given by the authorities is incomplete. This is the data that's given by the CNSC, and those are the chemical symbols of various radioactive substances inside the liquid. And it lists 21 fission products and 7 actinides. The 7 actinides are on the right-hand column. Just a word of explanation. A fission product refers to a broken piece of uranium atoms. When the uranium atoms are split, you get all these broken pieces. And so you get things like iodine-131, cesium-137, krypton-85, strontium-90, barium-137. These are all fission products. Actinides, and by the way, fission products are usually much lighter than uranium. They're between 1/3 and 2/3 the mass of a uranium atom because they're broken pieces. The actinides are either the same weight as uranium or heavier. So you get things like plutonium and neptunium and so on, which are heavier than uranium. And they're produced by the uranium atoms absorbing neutrons and getting heavier and turning into new elements. Now here's a list from the DOE, the Department of Energy, and it lists 13 fission products and 8 actinides. And when you look at this list and compare it with the previous list, which had 21 fission products, you find out there's only 5 fission products they have in common. So in other words, both of these lists are obviously incomplete, and they only agree with each other on 5 points in the fission products. The actinides are pretty much the same. I also, during the court case that we had recently, we discovered that AECL, Atomic Energy of Canada Limited, which actually runs the operation and produces this liquid, they had a list which had 123 fission products. So obviously, we're not getting complete information here. And so all the estimates that we make about toxicity and radioactivity and so on are, by definition, underestimates, because we know that there's a lot more there that they're not telling us about. Now, I have done some calculations, and pardon me for all these numbers. I know that numbers are not the greatest thing to look at. But what I've done is I put the names of the radioisotopes at the left-hand side. These are basically the fission products. And then I've used what I did here was this. I wanted to figure out how toxic it really was. So I said, let's take a large reservoir of water. And I chose for this the Washington, D.C. water supply. Washington, D.C. has a reservoir called the Georgetown Reservoir, which contains 530 million liters. And my question was this: what happens if you dissolve just 1 liter of this liquid in such a reservoir? So if you pour 1 liter in and somehow magically mix it through the whole reservoir, which of course it's hard to know how that would actually happen in practice because it would be a slow process. But if you did mix it in, it would be way over any limit that would be acceptable in terms of radioactive contamination. The whole reservoir would be rendered unusable. It would be undrinkable. And what I've done is I've calculated using the Environmental Protection Agency limits. That's the left column there. The limits on how much radioactive contamination you're allowed to have before it becomes undrinkable. And I've got those limits there. Some of them are blank because they don't have a limit for those. They just didn't consider it. Then I've got the contents of the FIS tank according to the CNSC and the DOE as to how much radioactivity you have in every liter. And then the next 2 columns of the annual radiation dose, I calculated from the CNSC figures, you get 1910 millirems. Now the maximum allowed is 100 millirems. So we're talking about 19 times over the maximum limit. And in the case of the DOE figures, we've got about 14 times the limit. And if you combine the 2 of them, you get about 31 times the limit. So the point here is simply that by using simple arithmetic, you can show that this material, 1 liter of it, would be enough to ruin any city's water supply. Now, about the cask, when they talk about transporting it, they want it to be safe. And of course, they always imply that it's absolutely and perfectly safe. Under normal conditions of transport, they have certain standard things that they look at, certain standard insults. And under accidental conditions, they have a drop of about 30 feet, that's 9 meters, not 30 feet exactly, but drop from 1 meter onto a punch bar, so you get basically a penetration. Then you can have an all-engulfing fire at 800 degrees Celsius, and you can also have immersion under 15 meters of water. So these are the things, the standards that they're supposed to design the cask to be able to withstand. In actual fact, these tests have not been carried out physically. They're done by mathematical modeling. So how the cask will actually perform in reality, we don't really know. The same company that manufactured this cask has manufactured other things that we have used at Chalk River. One of them is a caddy, and it's for solid spent fuel, not for the liquid. But they were using one of these caddies just recently, a couple of years ago, and when they lifted the caddy with the irradiated spent fuel, very radioactive, out of the pool, the bottom fell out of the floor of the caddy. And the reason was because of bad welding. There was another case where when they put the caddy material into a thing called a basket, they were lifting the basket with a remote controlled crane, and it failed and dropped the basket. So we have experiences of bad quality control with this company. So therefore, you really can't take anything they say on faith. Now, Marvin Resnikoff put my name on this paper because I helped with the editing, but it's really his work about the cask itself. And one of the things, and he drew on material that was published a long time ago, but this cask, remember, is 30 years old in design. And there were studies that were done decades ago that showed that if you have an impact at the end of the cask, it's pretty good. It's pretty able, because of those impact limiters, it's able to resist the impact. However, if you have a side impact, if for example, the cask were to fall off a bridge and fall onto the pilings down below or some rocks down below, and it hit on the side instead of on the end, then an impact as little as 12.5 miles per hour, that's the very bottom figure there, an opening as slow as 12.5 miles per hour could lead to an opening of the cask cavity. That's only 20 kilometers per hour. So the side impact is a weakness of the cask, and even the end impacts could be greater than we would anticipate. Now, once again, this is the same thing. I'd now like to focus on the fire. If you look at the fire, what they're supposed to be able to withstand is 800 centigrade fire for 30 minutes. But in actual fact, most diesel fires are around 1,000 degrees centigrade, and they often last for a lot longer than 30 minutes. Think of some of the horrible collisions that we've seen. And it turns out that, pardon me again for all these graphs, I know they're not much to look at, but basically on the bottom we have the time in hours. You notice the hours ticking by there, and at a certain point you get 1.0, that's 1 hour, and then you get 2 hours, 3 hours. It goes to about 3.5 hours, this scale. And if you have this fire raging around, a fully engulfing fire, then the temperature will go up, of course, inside. And what this is showing is the temperature in the lead. You know, the lead, I told you there was a lead shield of more than 3.5 inches. Lead gets hotter and the seals start failing. And then the lead melts and expands. And then you get, because of the expansion of the lead, it puts pressure on the inside cask, the inside cavity, and you get a cracking of the inner cask wall at a temperature of about 1,000 degrees. But that takes about 3.5 hours to get to that point. So you'd say, well, hopefully they can deal with the fire before then. But if you have 1,000 degree fire to begin with, instead of an 800 degree fire, it happens a lot quicker. And it turns out that you can start having the seals degraded after only about 40 minutes. And then the seals will fail before even an hour has passed. And then the lead starts melting at about 1.5 hours. And then before you get to 2 hours, you get a cracking of that inner cask wall. So these technical calculations are simply to point out that there are problems with the technology that we can't always anticipate. Now, those shipments are supposed to begin this spring, possibly this month, February 2017, because of the fact that we lost that lawsuit. And how? Well, as I said, 100 to 150 truckloads over a period of 4 years. And that's the end of the slides, but I want to keep talking here because for a little bit. I just want to point out a couple of important things. Number one, why do they want to ship this thing in liquid form? They've never done this before. Answer, it's not necessary. They don't need to do it. They can, in fact, ship this material. They can, in fact, ship this material I'm sorry, I lost my train of thought. What they've been doing since 2003, remember I told you the tank was full in 2003. For the last 14 years, they have been producing the same liquid material, exactly the same stuff, and they've been solidifying it regularly. So as they produce it for the last 13 or 14 years, they just spontaneously solidify it and store it on site. They could do that with the fish tank. There's no reason to transport it in liquid form. Second point, the whole purpose of transporting it, which is given, the primary purpose, is to get rid of weapons grade material from countries that do not have nuclear weapons. Not only Canada, but many other countries around the world that have acquired a certain amount of weapons grade uranium from the United States. And now the United States is wanting to pull this back again and get it repatriated. They call it repatriation. Well, that's all well and good. But what are they going to do when they repatriate it? It turns out that at Savannah River, at the Savannah River site, they're going to do a process called down blending. And what that does is it eliminates the weapons grade uranium by converting it into uranium that cannot be used for weapons. Well, it turns out that can be done at Chalk River too. You don't have to ship it down to SRS to do the down blending. You could do it right on site. In fact, last year in 2016, Indonesia, which has a smaller quantity of the same liquid, they successfully down blended it in only 3 months and eliminated all their highly enriched uranium. And this was with the full knowledge and consent of the American authorities. Same thing could be done at Chalk River. And in fact, we have a document from the Minister of Natural Resources here in Canada showing that they were in fact planning to do that before they struck this deal. So, question, why do they want to move it down to Savannah River site in liquid form? Answer, it seems to be a make-work project to keep that old facility, that reprocessing plant called the H Canyon that used to be used to produce plutonium for bombs. And now it doesn't have a raison d'etre. It doesn't have an excuse for operating anymore. It's very expensive. And it's a private company that manages it. And they seem to want to justify keeping it running, keeping it running, keeping it running. It's the only reprocessing plant left operational in the United States. So from our point of view, it seems pretty clear that it's basically just a make-work project, unnecessary, and shouldn't happen. Unfortunately, we went to court to try and force them even to have an environmental impact statement, and we lost that court case in January. The judgment came down in January. Basically, the judge didn't say that it was safe. What she said is they're not breaking the law, that within the law, they have the freedom to do this, and they have the authority to do it. And so for that reason, we can't stop them. Other developments in the Niagara Peninsula, thanks to the work of Gracia Janes and other people in that area, we have 22 municipal councillors who have unanimously objected to the shipment through the Niagara area. And we've also had the lawsuit that I mentioned to you. And we've also had Representative Higgins in the United States, who has introduced a law into the House in the United States, which has passed the House, but it hasn't yet passed the Senate, which would require a complete review of security from the point of view that terrorists might attack such shipments in order to cause a huge incident that would be extremely costly and embarrassing. So I'll stop there and leave time for questions and answers, and I hope that I've laid out enough of a picture that people have something to go on. Thank you.